So 3, 2, 1, it's on the record now. Okay. All right. This is the classic example, and this kind of load case is real because when you have the wind load, when the wind blows in this direction, you know, this face of the building will be hit by the wind, but it's not just there because the wind can suck up your structure. So you can have suction like the upward pressure like this, and on the back, you know, you also have the force going in that direction. So this is no joke, and it's a situation that you have to face from time to time. And to calculate the real wind load, you need to go and look at the standard of the Department of, I don't remember the English name, but the Public Works, yeah, something like that. Okay, so the load case is real, but say the numbers that I use here may not be as accurate. Okay, so for this case, it's not really difficult. It's just another case just to show you that how to deal with the load. But you see, we now already have the load that is perpendicular to the member. So things become a little bit more difficult. One moment. Okay. So it becomes a little bit tricky when you calculate the reactions, okay? Because say when you take the moment at this point, let's call it A, you're gonna need these components to be, say, the one that you can calculate the moment more easily. So you need this component to multiply with this distance. And then you need this component to multiply with that distance. Okay, and likewise with this. But for in terms of the uniform load acting on the member, it's already easy enough because they are already perpendicular to the members. Okay, so let's say I am giving the load in terms of kilogram per meter, but in the calculation, I think I'm gonna go to the ton unit. Okay, so I'll try to squeeze this within our time limit. It's point A. So I think it's better to use a different color, maybe. So erase this, all right, and let's name that A, B, C, D, and E. Okay. So now I can take sigma MA equal to 0. Okay. So now we have this first uniform load, which is 0.3 multiplied by 6. That's 6 meters there. Square over 2. Okay. Now let's go to the second component now. We need a little bit of our trigonometry magic. So let's take a look at this triangle. Okay, that's 3, that's 6, so that's 3 square root 5. Okay, and just for the sake of simplicity, the angle, the theta is 26.57 degree. Okay, not the radian. And we have that. This is our angle. So the first one, if this is the angle, that's the angle. The similar angle. So we the sine component will be the one on the horizontal, and the cosine component will be the one on the vertical. Okay. So for the sine component, it's going counterclockwise, so it's the same. That's plus 0.15. And then the total length, okay, it's 3 square root 5. That's a total force. So take the sine term to make it the horizontal component, sine 26.57. And the center of the load now is, of course, at the middle of the member. So the height or the moment arm becomes 6 plus 1.5. Okay. And then the vertical component also gives you the counterclockwise moment. So it's 0.15 multiplied by the length again, but this time is cosine 26.57. Okay, and oops, there's no parentheses, and it's at the center. So the moment arm is now 3. That's the end of the second load. Now we go into the third load. Now, if you see this one is giving you the clockwise moment, so it has to be the negative sign. So pardon me, I just write positive ahead of time. That becomes negative. And you have 0.35 instead, and 3 square root 5 as the total length. And that one is a sine term. I'm just going to skip 26.57, okay, because I'm running out of space. And the moment arm is again the same, 6 plus 1.5. And then the vertical component, this one, it gives you again the counterclockwise moment. So this one becomes a positive again. 0.35 multiplied by the length, 3 square root 5, cosine 26.57 multiplied by 9 this time, right? Or maybe I should be more discrete, okay? 6 plus 3. I thought I'm running out of space, so it's just like too close. Okay, right? And then the last one, the easier one, another counterclockwise moment coming in from this load. So it's plus 0.4756 square over 2. And then let's say we think, you know, everything is going counterclockwise. So it's safe to assume that, you know, our RE may be going downward. So let's say minus RE multiplied by 12, okay, equal to 0. It's a bit long, and then yes, as assume RE is equal to 2.59 tons. You know, the exact number is 2.5875. But you can, when you work as a true engineer, even though you may use this number in your calculation, but when you write this, okay, according to the significant figures, to write something like this is a little bit too much. It doesn't make you look good. It makes like, oh, why do you want to count something like this? It's like you're measuring your weight in, say, milligrams. It's a bit silly, okay? And now we have RE. We can proceed to use sigma ME equal to 0. This is a better one to use to check yourself. Or sigma Fy equal to 0. Okay. Keep in mind that if your RE is wrong, you use sigma Fy equal to 0, the rest is wrong and it becomes garbage. Okay. And therefore, you know, whichever way you use, let me speed things up a little bit. RA is another downward force of 0.412 tons. the exact number is 0.4125. Okay, and the simple enough one, sigma fx equal to 0. That's going to give us, do I need to do this? But, you know, be careful that you have your horizontal components from the roof portion as well. So maybe it's better to show you. So you have 0.3 plus 0.475, right? The two basic horizontal loads multiplied by 6 plus or minus, because, you know, say, okay, we have two going the left, this one, so let's add that one. Plus 0.15 minus 0.35, right? 3 square root 5, I suppose. Yeah. And sine term, 26.57. So that gives us the horizontal reaction equals 4.05 tons going to the right. Okay, one second. Okay, so with that, now you can easily proceed to you know, finish everything off in the same manner. Okay, so let's look at the first free body diagram of member AB. Okay, so this is member AB. And now we have 0.412. We have 4.05. Okay. And you have the uniform load, but it goes this direction. Okay. So you can say sigma Fy equal to 0. We shall give you the H. No, I'm sorry, not H. The let's call it. Oh, it's difficult, right? Because you can have. It's vertical, so let's call it VB. Equal to 0.412 as well, right? So that's the result. You know that from your equilibrium. And then sigma Fx equal to 0. So you have 4.05 minus, that's 0.3 multiplied by 6. That's minus, so if I call it V, so that way HB equal to 0, right? So HB is now 2.25 tons. So that is that. So the last one is the moment. So let's take sigma, not that sign. Okay, sigma MB equal to 0. So that would be MB should be equal to 4.05. I'm assuming that one would give a larger moment multiplied by 6 minus the moment due to the uniform load, which is 0.3 multiplied by 6 square over 2. That is 18.9 ton meter. See, that number is pretty large compared to the load, which is only in hundreds. Okay, and this is the moment. 18.9 ton-meter. Okay, now the fun will begin with the free body diagram of member BC, I'm sorry. So we have BC here. You already have this load. Watch the direction, okay? It's that. And we have, let's say, I give that one the red. I should give this the blue. Okay, that's 18.9, right? And if that one goes to the left, this one comes to the right, 2.25. That one goes up, so this one comes down. 0.412. Okay, so again, you can complete your free body diagram in the, say, global XY axis. Okay, this is a global, I mean typical XY, or your local XY. In the previous problems, we used the global XY because we have the force in those directions, okay? But this, we have the force already perpendicular to the member, so maybe it's a bit easier to do it in its local XY, and the local XY, that would mean in this, okay? X prime, Y prime direction. So that means I probably need to calculate the force in this and in that direction. Okay, so okay, got a problem with naming the stuff, right? But have we worked on the trigonometry? I think we have, and we use this as our angle. Okay, so I'm just going to come back and use the same. So this is going to be my angle. But if that's my angle, that means this is my angle, right? And that's the angle. So that means this vertical component let's say VB, this VB is going to be equal to, this one is a sine component, right? 2.25 sine 26.57 plus 0.412. This term is cosine 26.57. So you better be careful with your trigonometry, okay? And think about the fact that this is like the high school stuff. So we're not doing anything new here. Okay, just put the forces in the same direction. That's all. And this is 1.375 tons. Okay. Okay, so that is 1.375. Okay, and we can do the same to obtain this one. Okay. Oops, I thought I changed the color. Missed it. This one, let's call it HB. Naming things, it can be tricky. I thought that we use AB as a baby universal, so it may be wiser to try the prime on it, just to know that, okay, we are dealing with a force in the direction, local directions, okay? This one is HB is the, say, 2.25 cosine now. Okay, 26.57, but this time is this force is going in the opposite direction, so you have to, you know, subtract it. 0.412 sine 26.57. That gives me 1.828. Okay, that is, do we have more space here? Oh yes, 1.828. Okay, and you know, some of you, if not many, will go on to, you know, pursue higher education in masters, maybe in structure and stuff. And you may have to deal with stuff like this, say, more often. So it would be better to try to say establish, you know, something firm from the very fundamental. So you may want to say you want to use sigma f x equal to 0, but this one is x prime, right? Because you're looking at the force in this x prime axis. With that, you have hc prime is also equal to 1.828. So that's the one. That's 1.828. And okay, what do we have left? You can complete this VC prime by using the sigma. The erase first. Sigma Fy prime equal to 0, because you already have this load. Okay, so that is going to be 1.375. You have more space? Yeah, I have more. Like that. Minus 0.15 multiplied by the length 3 square root 5. Okay, that is my VC prime, and that is going to be equal to, see my own handwriting, I believe it's 0.369. Okay, tons. We have only like 5 minutes left, and I think you have the idea. So for fear that we may not finish this on time, I'm just gonna try to finish the shear force diagram and bending moment diagrams for these two members first. Okay, knowing that if you are dealing with, because this is half of the system now, so let me go back to this. Say I have done AB and I've done BC for you. So to do the ED and CD, to try to work your way from BC to CD is difficult, because now you know your free body diagram of BC, it's in its own local direction already. But if you want to finish, if you want to keep going in this direction, it means that you have to change the axis for these two into this, which is difficult. So it's better to work from, you know, right and then meet in the middle. Okay, so now let's say we are missing something, that is the moment at this location. So I'm running out of colors. Sigma MC prime equal to 0 to get the end moment. Okay. Oh, don't forget that you also have this moment. So 18.9. Okay, plus the moment from that shear 1.375 multiplied by the length of the member, which is 3 square root 5, minus moment due to this uniform load, which is 0.15 multiplied by 3 square root 5 square over 2. Okay, that is your MC. And this is equal to 24.75 ton meter. Okay, so that's the moment. 24.75 ton meter. And again, I like to finish the diagrams for these two. Okay, and if I could, I may. I don't know, but that's kind of difficult. But I'll try to do it. Let's try to record the rest. But anyway, be mindful of one thing, because this time your uniform load is not in the direction where you are familiar with. So you have to be true to your free body diagram. Okay. So let me go to the new page. And can I do this? Copy and then paste. Okay. If we have that. Okay. Now let's say this is okay, A and B. Now your shear force, it's downward. So I'm going to skip the calculation part. Okay. So this one is down. So it's 4.05 minus, but you have the upward uniform load, so it goes up. So that is the up on the right, so it's minus as well, minus 2.25. Okay, that's your shear force diagram. And for your bending moment diagram, that's downward, so it's negative, or minus 18.9 here. But your shear is also the negative area, so it brings down to meet this value. But you can see we already discussed that like an hour ago, that if you look at your shear tends to go upward. So in the end, your moment will tend to increase. So that's why your curve is going to look like this, and then just keep increasing if we continue on. Okay, so don't follow your routine and say, okay, got the bending moment diagram, just curve must be like that. The curve is like this due to the nature of the uniform load. Okay, that's a bending moment diagram in ton meter. This is in tons. Okay, and we have one more. Hang on. This is going to be a mess. If I can lasso this one. So, okay, so just to answer your question, you don't need to say turn your members or anything. You can just keep drawing your diagrams. And this is a downward shear, so it's a negative value coming down like this. And then you have the upward uniform load that goes up. Okay, that's 1.375, and that's minus 369. But your bending moment, this is shear force diagram in tons. and your bending moment diagram, they are both negative moments, you see. That is minus 18.9. And then that is minus 24.75. Please notice the direction of the moment, okay? It's like this. So that's basically negative moment. And your shear keeps going up. So your curve, it's going to be something like this. Okay. That's a bending moment diagram in ton meter. Okay. For the two members that I haven't finished, you can again work your way from this up, okay, ED, and then go to CD, and the nature of the diagram should be similar to a CD should be similar to BC, but DE should not be similar to AB because of the difference of support, but should not be much different because it's a roller and a hinge. Okay, so that's it for today. And one more thing, I have given you this, but it's not going to be an exam and stuff like this. I wish to explain this to you, but maybe I'll do it in the future. Okay, it's a system of the roof that you should know. It works the same way as the system that we talked about before in the typical floor system, but it just, instead of having the primary beam, we have a truss that acts as a primary beam. That's all. Okay, so let's not worry about this yet, and we'll find a time to discuss about that maybe after midterm in the class. But for the time being, that's it. That's it for you. Okay. Is there any question? Oh, so awfully quiet. So okay, question in the chat. No, that means crystal clear, right? So let me stop the record.